This talk is about ladder programming and structured text programming, and the context is in ISaGRAF. We will have what I'm going to do is show first the ladder, and then we're going to take a brief look at the programs as they've been written, and then basically start over and rewrite them ourselves so that we can see online how the program is created and how it works. So first of all, here's the ISaGRAF project management, and a note that I'm running it in Windows Virtual PC because I have a Windows 7 machine, and this is required for running the ISaGRAF 3.5 environment. Now let's see how that window starts. I've simply made a shortcut in it, and one thing for ISaGRAF programming is remember what window you found things in. That's, to me, was the biggest challenge, was what window am I using to do such and such. So here we've defined, there's a default project that always comes, and then I've defined 3 other projects. Let's look at this very simple ladder program first. We've got a function block here, and we've got, I believe this is actually just a function, and it is a block, not the same as a function block. And here we have a simple ladder program that calls that function. And I wanted to show that users can define their own functions in ladder with this little program. So we can run these in the simulator and see what they do. This function, all it does is increment the number that comes in. And this one down here is just a static link. Really, everything going into it is a constant. The do add, I can set true. So this actually has 2 outputs. It has a Q and it has a numeric integer output. And we can force it false. Let's have a look at the function. The enable here is something that lets us decide whether or not the rest of the function is going to work. And this happens with this return item here. The way these ladder programs execute is first you do one rung and the next and the next. And they work like Boolean Logic, similar to wiring relays, where you have one rail here. You've got to imagine a continuous line, and one rail here on the right. Here we have contacts on the left, and we have coils. This is symbolic of a circle that are outputs on the right. Now we can have 2 outputs. In this case, we're outputting to the function, and we're telling it if this is red, in other words, if this evaluates true, that we're going to exit. So now let's go ahead and write this ourselves as a new project. So I'm going to stop the debugger and close the project, and we're going to call it F in L2. Which means it's a function and it's in ladder. So first thing I always do is set the comment text so that when you have 30 of these projects in here, you remember which one it's about, and this is okay, so let's double click on that line. Now within the project we have a list of programs here, programs window. So first thing I'm going to do is make the function. So I'm going to go to new, I'm going to make it quick ladder type. Now, I'm not 100% which of these I clicked yesterday. I think I did function. So let's call it incrementer. In this version, we're limited to 8 characters, and you may find that in all versions also. So conditionally adds 1 to the input number. Now, what is important about functions is inputs and outputs. Now, if there are no inputs and outputs defined, you're going to find an EN for enable appearing on the left of your function block and an ENO appearing by default, even if you have other analog functions, just because we require a digital in and a digital out for any function that's on the run. But what I'm going to do is specifically create a digital input. Call means that it's coming into the program, Boolean, and it's going to be the first one, and we're going to call it enable instead of just EN, which is a reserved default keyword. And so there's that input. Now we're going to create an output. That's a return. And we're going to call it steady. What did we call it before? I think we called it just Q before, and let's stick with that. Let's peek into our other program and see how we name that one. Here's an instance of it, and let's stick with Q this time. So we're going to close that project so we don't get them confused. They're going to look a lot alike. And again, avoid the project management window, go back to the project window, and so we're going to have a return value that's Boolean. Click OK. Don't know how I got away with that one before. We're going to go with calling it the same as the program, like the error message said. Now I want to have an analog integer input. We're going to call it InValue. Call means it's an input. Analog and insert. Need to click insert first. Analog again meaning integer in this case. And let's make another one that is our output. Let's call that one sum. Again, it's another analog. So we're actually having two outputs from this, and we're going to make it a sum as a return. Increment is one output, and sum is one output. So now we've finished defining our inputs and outputs. Let's make one of these as a function block. I think that's where the error is, that it's telling me to use the same name. We're going to call it a function block. We're going to call it add1. Notice it appears in a different category with this line separating it. And You can choose your language type at the beginning, and what you don't want to do is forget to do that. Oh, I got a different language than I intended, and you could tell that because the icon didn't look like these contacts and coils. And it is going to be quick ladder. That's what we forgot before. And it's going to be a function block, meaning there are instances of it instead of something that is used over and over. When you use it, each time you created a new one with a function block. So let's go on in here and define our inputs and outputs. We've already got an output time called cube, but I'm going to make it a going to call it sum. That will be our analog result, and we're going to call this output did increment. It's going to be a Boolean, and it's going to be a return, making it an output. Make another one. Enable. All makes it an input. Boolean makes it our first default one, so it's going to be replacing the default en variable. And finally, we're going to have our analog input value. That's the thing that we're going to add 1 to. So we've got 2 inputs and 2 outputs. 2 analogs, 2 digitals. Now it may complain about the order that these are in. It does. Use a range function. So we do this, and it puts them in the required order. Now let's see what that looks like when we insert it in a program. This one. Get rid of. Now, we're going to make a new program that uses our function. And we don't want a function block diagram, grub diagram, we want quick ladder. And so there we go. We have it. We can push F6 and get a new rung with a function block and a coil. Now we want to choose. It may or may not show up before we've compiled. Let's see if we already have the choice. Add 1 in here. We do. No comment on it. That's not very good form. Okay. Interesting. These were supposed to have been supplanted, so I'm not sure quite why that happened. I'm not going to worry about that right now. Let's just go ahead and put in the functionality in the function block. Here we're going to put a new rung. Added a contact associated with the variable. Now, one thing about ladder is you can make contacts manipulate the values of their variables. By pressing the spacebar, we get this backslash, and that means not. Now here we're going to put the, and so if we're not enabled, then we want to just jump out or return, exit the whole function block without doing anything. So we can add this return value there. So if we're not enabled with this variable, we're going to return. Now let's make another function block. And here we're going to actually do the addition. We're going to put a constant here. You say, where do we choose constant? You just literally type the constant. And we haven't defined any variables, so we need to do that. No. In this case, we've defined our inputs. And I believe it is called inval, I-N-V-A-L. We want the result to go to sum. So if we're enabled, this will come false and we won't exit. And we don't need that coil for anything. Actually, we wanted to return the value, so I'm going to put the coil back. And that was going to be the output value called debugging. So I believe that's everything that we wanted to do in here. So let's exit. It's going to ask us, do we want to save? Yes. Do we have any notes about it? No. And let's see if we're at a point where we could actually compile. I believe we are. Let's just do that to see that we have no errors. It's showing us that we didn't define anything here. So let's go ahead and define some global variables. We're going to have, let's call it index, and we're going to initialize it as 0, which is defined. It's going to be an integer, and it's not going to be Modbus accessible, so no network address, so that's our value there. And we're going to use, we need to save that. Have Boolean internal. Actually, I want to call it steady. Never mind. Let's keep it parallel with what the function block was defined as there. We want to choose our type as analog for this line, index. The output is also going to go to index. Okay. Okay, the programming process is taking longer than I rehearsed it, so what I'm going to do is, if it's okay with you, take another 5 minutes here, and we're just going to review the other program rather than rewriting it. Now we succeed in getting our compile. So let's do a simulation of this. Now we can click on this to see what's going on. We have index 0, incremented coming out false. Do enable false. Well, let's enable it. Force it to true. And now you can see that the number's going up. Now, you might think this only executes once, but in ladder programming, each cycle of the PLC executes every program in the begin area, and in every program it goes through every rung until you hit a return or a branch or something like this. Now the one thing we didn't see was how to eliminate those default values here. I had intended that enabled and did inc were going to replace these, and it didn't work today. It did work yesterday. So let's look at the version that I had yesterday. This is the original one. Ladder function. Again, we have the not enable, and I called it Q. Perhaps that had something to do with. Let's look at what the inputs and outputs are. The very first thing is a digital input, and the very first digital output is this Q. And here we have, actually we added 2 in this other program, not 1, which is still a case of incrementing. And so we have add me is the 1 input plus 2 is the output. So it's just different variable names for a very similar function. Now let's see how it's called. Notice that here we only have 4, which was the goal, was to eliminate those extra 2 at the top. And here we have do add and is steady. Notice that we made it a not version of increment here. Because we have not, and then it goes to the output. So let's simulate that one. Let's have a look at how this is working here. Do add is false, is steady is true. That's because in our function block, so I'm going to use this so we can see both of them. We have this not type of contact here. So the false do add becomes true once it enters with that type of contact. So let's make do add true. And now you can see is steady is false. It's not steady, it's increasing. Down here we just had a little bit of, this just demonstrates a typical ladder. You can have function block here, and you can have 2 contacts in parallel form an OR, and then the experimental result is shown there. So now let's do something a little different than simulating it. I have a PLC here, and I've defined it to be connected by Ethernet and set it up to this particular IP address earlier. So we're going to connect. And I do need to plug in the PLC. And I need to disable Econ utility because, no, it's fine. It's not. It doesn't have a dialog open. So it is not using the same comm line at this time. What I have wired is a 7188EG PLC, and its serial port runs to an analog input module, and then it also runs to a USB to serial converter, an I-7561. So we can't have 2 masters on the bus. That's why I came over here to make sure that Econ utility was not polling this module. Here you can see it found it earlier at address 9. I ran into this yesterday. ping. Let's restart everything here. Sometimes you get problems when it fails to connect. Okay, this time it connected right away. And you can see that the other program is running. So this is different from in simulation. This is really showing what's going on inside the PLC. I want to stop the running program, which is that loop array program. Now it says no application. Now I'm going to download. Notice we had two choices, symbols and tick code for Intel. I know that was really quick. But we did, when we set up that project, if we want to do anything more than simulate, we need to tell it what type of processor the CPU has, and we told it Intel. This is something I did yesterday. I didn't do it in the other demo program yet. So now you can see we've got a little window showing us what's going on. And this is following what's actually happening in the PLC. Now we're going to turn this on. Notice how very much faster it increments when it's running in the real PLC than when it is running in the simulator. Up here in our debugger window, we can see that it's taking either 2 or 7 milliseconds. The longest it's taken is 7 milliseconds, and that is per cycle. That means that it's doing this rung and that rung every 2 to 7 milliseconds. And when it hits this rung, it is also doing this other function that we defined. As well. So it's really doing 4 rungs in that speed. Now let's look at that other program. Stop debugging. Stop that. And I wound up closing my projects window too, so let's bring that back. This is a ladder program where I wanted to show that we've got loops and arrays possible in ladder. Notice this symbol here. Notice that symbol down there. This symbol allows us to branch back to the beginning of our loop. So quite often in ladder you don't bother with loops, or in PLCs in general, because the process is going to repeat every time. But in this case, I wanted to demonstrate what arrays do. Arrays are variables that have multiple elements. See how this one here has an index range. These others are just integers. This array is also an integer, but it's defined with a dimension in here. This is a quantity of how many integers it has. Let's look at what the loop does. And the intent here is to show how each of these is actually separate values. We are going to set a counter at the beginning of this loop, and then we're going to look to see if we finished running our loop. It keeps coming back and forth from here to there indefinitely until this test is false. So we're using greater than or equal block. If index is greater than or equal to loop limit, we will go to loop done, which is this thing here, which essentially just exits this program, and if there are any more programs in our project, it would go ahead and increment them, in this case one called furnace. So that's how we get out of the loop. We could also put more rungs down here. Now suppose this is false, then we're not going to go to loop done. This Q here is going to come out false. We're not going to execute the loop done jump. This is called a jump, and that's called a label. We're going to go run the next run. And first thing we do is we're going to increment, here's the comment, one element of the array. we're using the add. We're going to add 1. Now look at this here. This is telling us which part of the array we're starting. We're going to be writing into. We started with, this is a 1 gain block. It's essentially an assignment. We started with putting 0 into index. We did a test here. Is 0 greater than or equal to loop limit? And we haven't gotten into what loop limit is. It really should be anywhere from 0 to 5 loops. And so index here, the first time it goes to the loop is going to be 0, and we're going to modify the first element of that array. Again, as in the other program, the input and the output are the same variable. Now, that doesn't necessarily have to be the case. So this will add 1 to the 0th element of the array in the first loop, and it'll add 1 to the second element of the array in the next loop, etc. This here is another increment. It just increases our index so that eventually this test up here will fail. Let's watch it run in the simulation. Now, the loop limit is 0, so this is called a SPI list. It allows us to see individual array elements and variables of different types. In this case, we all have integers, but we could have also have had Booleans here. So this is a little debugging aid that you can set up for each program that will let you see what's going on. What we're going to do is force loop limit to be 2. The loop is going to run twice. And that means it's only going to increment the first 2 of the my array values. So let's write that. Now you see how these are going up and the other elements of the array are staying the same. Let's let the loop run a little bit more. This shows that we really have multiple things happening in each pass of that program. And the program is passed again and again. That's why we see the numbers go up forever. Let's make that a 3. And now you see this one also begin to increment. So that's what I wanted to show what an array is. It's a collection of values with one name that you access with a number. That number that was defined in here. Not only did we type the variable name, we had these brackets and we had another variable name in there. And we have to keep this, at least in this 3.46 version of ISaGRAF, we have to keep it down to 16 characters. The usual 3.55 that people are running allows somewhat longer expression. So I had to make sure that both these names were relatively short ones. I'm not going to make any changes. Now, we were going to discuss here also, let's write this in ladder and then let's look and write the same thing in structured text so that we will have something in structured text. This is, again, you see this is not ladder. This is some other type. So file, delete. File, new. This is going to be basically a thermostat program. So rather than an industrial furnace, let's pretend it's a home thermostat. That's all I can type, 8 characters for the name of the not function block diagram or the ladder diagram. Okay. Now I believe I already defined some of these variables in here. I have a furnace temperature. Now let's call that room temperature. Temperature as real. And we're going to have the same thing, room temperature as an integer. And it's going to be coming directly from our input module. But for the moment, let's not worry about getting the data. Let's look at the logic. And this is just to see say current modifications. I want to show you typical use of ladder, relay ladder type logic. Now, in a home furnace, we have a pilot light, so we're going to define that as a Boolean. This variable would be true if the pilot light is on. That would be some sort of a bimetallic switch. And so let's define another variable. And call that fan motor. And this is used to the thermostat. Let's consider we're only heating. You can have the heat on or off, and you know that the fan always follows when the furnace is running, unless you have a little auto or on switch, and we're going to simulate that too. So the fan motor is a separate thing we're considering, and we're going to have the burner gas, and this represents turning on the main gas valve. And again, these are all internals. They're not associated with any slots in the PLC. And also, we would still have them be externals if they were associated with remote I/O. This auto Boolean is going to represent that auto on-off switch on the thermostat. And we're going to not pay any attention to the heat off switch that would also be on the thermostat. Yes, save modifications. Now, in our thermostat logic, let's just start by having edit, insert run. Now, let's put a comparison function here. Let's have a less than, and this is where our temperature is going to come in. If, and we're going to go to analogs, room temperature is less than, we didn't define a set point. Save so that this should know about it. So if room temperature is less than set point, this is going to come on. And we want, we did want a contact because we wanted an and. We only want to turn on the main gas burner. If we have the pilot light lit. That's a safety function of any furnace. So then burner gas right there. Now, so this controls the fire inside our furnace. Now let's make another rung to control the fan. And in this case, we want the fan on if the gas burner is on, or if the on auto switch is not in the on position. So we're going to go with contacts here, and it's going to be an OR type relationship. So we've got two of them there. Here we've got auto, and we want it if auto is not the position, so we hit the space bar and make it a not type contact. Or if the burner gas is on, then we want the fan motor on. So this is ladder of a simple thermostat. And you can see it's a pretty easy program in ladder. Now since we're running short on time, I'm not going to bother attaching the I/O module, but let's compile this. Let's do it again because I want to point out that warning. Make, verify. Make, touch. Make all files ready to compile. Look at this warning here. Backward jump detected. That's our loop. It warns us that we could get stuck in an infinite loop, and then what happens in that case, if your programming is wrong, you get stuck in the loop and you never progress to the next PLC cycle. So if you're going to be doing looping in ladder, you've got to put up with that warning. So let's do this again in our real PLC. Download the revised application. Really, we have two completely different functions running in one program here. Here's our SPI list again. Now 0, 0, not greater, they're equal, they're not greater than, so the pilot, we don't have a pilot and we don't have burner gas. So let's go ahead and make our set point 25C, and let's make our room 20. So 20 is less than 25. Pilot on is false. Let's say that the pilot light is lit. Now finally our burner gas went on. And down here we're still in auto, so we didn't have the fan motor, but now we have the burner gas, and now we do have the fan. So let's say the room warms up to 26. And even though pilot is on, this is an AND situation. We need the result and the pilot before the burner goes on. And so burner gas is off. Fan motor. Well, auto is false. Okay, so that means we're in the on position of that switch, and the fan motor is still on. Well, we want the fan motor to stop, so let's put it into auto position of our switch, and now the fan motor finally stops. So I'm going to conclude with a a structured text program that does this same thing here. So we're going to call it T2 for thermostat, the second thermostat program, and we're going to make it structured text this time. And we're going to just make it there. Now, let's bring up both so we can see the comparison between the two. All right. Now we have no text in here. So what we're going to do is write the equivalence of that. We're going to say, we're going to write a Boolean expression in text. You're going to assign the result of burner gas from a Boolean expression. It's going to be something in parentheses, which we haven't defined yet, and pilot on. Now we're going to put our expression in the parentheses here, which is going to substitute for this function block here. And that is room temperature less than set point. That's our complete expression that replaces this one rung. And one thing I like about structured text is that it's a little bit more compact, but you really need to add some comments so it's more obvious what's going on. So you're going to say, and I'm going to describe it. Is room too cold? And is lit? Question mark. So that determines our main gas burner. Now let's take care of the fan. Our question is going to be, and notice we're using an OR here. This arrangement here was an OR. And this not comes from this little backslash there. So let's write that expression right here.
Oh, if we do the discrete, probably. That would be a help, but if we do the PLC, no. Oh, the fourth, yeah.
It's not case sensitive in ISaGRAF, but I make it capitalized. It's a little easier to see the two words. So this line here, not auto, not is the backslash, or is the fact that they're in parallel. Burner gas, there's the expression for these, and the result fan motor is the assignment with this right here, and there's your fan motor value. So these are two equivalent programs. Now let's get some, let's show how you save a program also. This loop array is the name of our program. Loops and arrays with thermostat.
Okay, fine.
Suppose your program wasn't working correctly and you wanted to get some help with it. Or you just want to save it so you have the old version to fall back onto if you want to. We do this, and notice we're in the first window that came up, Project Management Tools. And here we are, loop array, and we say backup. That was fast. It made a single file, and it's called loopara.pai. I'll show you where it is. C drive, and I've chosen to archive into the standard place, ARK, and so we should find a file here called loop ARA, and there it is, and it was backed up at 1:59 California time. So we can close that. Now, what I'm going to do is disconnect the PLC so that now the PLC input, any input it might make to the serial line is, actually we don't have to because we haven't defined, we're just going to leave the PC and the PLC sharing the serial line right now and go run, it's an RS-45 line so they can share it. We're going to run Econ utility. The address is 9, so it takes a little while to show up. And we can pause further searching. This is a universal analog I/O module that's on here. and I've set channel 0 to be type K thermocouple, and I have previously wired that to a voltage source so we can simulate a value. Let's look how that works. The voltage source is in another ISaGRAF program. We can debug. This is just an analog output module put into a slot type PLC. 16 counts of out of 32,000 were set there. Let's see what we have. Could someone mute their microphone, please? It's showing 29C. Let's go and force a little bit of value back here. There. 0. Let's make it 200 counts. Right. And let's look at Econ utility. And now it's showing 711 degrees C. The room is on fire. We don't like that so much. So let's go back and get a more moderate value. Let's try those 16 counts again. I think maybe it just hadn't written before. Let's go back and look. Nope, 29. So let's see what 15 counts gets us. Being a thermocouple, it's very sensitive in the millivolts on a plus or minus 5 volt range. Notice that I'm jumping back and forth between Windows XP mode and a Windows 7, so an application that's running under Windows 7. It stayed 29. That's interesting. Let's goose it a little bit more. Okay, now we have a room below freezing. Let's we'll accept that that means the thermostat has to go on. So let's cut out Econ utility so that we are not contending with it on the bus. What I need to do, though, is look up the range configuration tables. We've chosen type K, which is here. And we see that it is minus 270 to 1372. So we're going to leave that open. And right, there's another table, but it shows you. This is the table I was after. It shows you in more detail what numbers you get. Now we chose engineering units on Econ utility. No, we chose 2's complement. So we want to look, and you do need to do that for ISaGRAF. And you'll see that this is the range, full scale range, 7FFF. So let's make a note of this. 7FFF is 32,767 in decimal. And it equals, again looking in the table, 1372 Fahrenheit. And the bottom of the scale is minus 270, but the trick to know here is that 0 equals 0 on all these thermocouple ranges. And if you did the linear plot, you would find out that that's how that gets. So let's go back and exit this so we're not, again, we're not contending for the serial bus. And go back to our virtual PC, and we will just save this where we can, I think we can see it there. Okay. Now this other application running in another PLC, we're going to hide that for the time being, and it's going to continue running in that PLC. Now, let's go back to our program that has the thermostats in it. We're going to define an interface to our external I/O module, and it's going to be a serial interface. I choose bus 7000B. It means it's for 7000 series modules. B has some more features than the implied A, and click OK. And now we need to configure more about. We're not going to use COM3. We're going to use COM2. There are only 2 COM ports on I-7188EG. It's not a slot type controller. Its size and shape is the same as the I/O module, actually. This one features Ethernet, and that's how we've been debugging it. I'm not going to use watchdog. I'm not going to use checksums. And this variable could tell us if the port succeeded in opening or not, which is a possibility it won't. So we're going to, yes, create a variable to monitor that. We're going to call it COM2 status. Now notice that it's not the module status. It's about the port itself. And cancel. We need to make this an input. This counts toward your tags. This ISaGRAF is operating in a 32 tag version. It means we can now have 31 more inputs and outputs. And it counts as a tag because it's in these slots, even though in this case it's an imaginary slot. It will count towards our tag limit. So let's look in the I/O connections, the slots, and let's associate this. If I hadn't defined it as an input, it wouldn't have appeared here to choose. And it may be important because I'm not so sure that COM2 is set up for working that way on this module. Let's verify it. All we've done is add that COM port so far. We haven't really associated with the module yet. Notice that we've stopped the dialog on Econ utility, so we're not interfering. And let's download the new version. Now, let's see how our COM ports. 9600 is the indication that it should be running just fine. It's telling us what the baud rate is. Otherwise, I believe it comes up as 0 if it fails to get to open the COM port. And what I was afraid was that I had it configured as an RTU slave port. Apparently not. So we know that we're good on that. So let's kill the debugger here. Now, I usually make a separate ladder program to associate variables to IOs. New ladder. Associate with not quite the full spell. Ladder diagram, main program. Inserted run with a function block. And we're going to pick our module name here. Notice that we've had to pick the COM port and the module. 7019, the R isn't showing. We have an address constant 9. And now we're going to use one of these here. We don't want a Boolean, we want an analog. And it's the room temperature as an integer that we're going to associate. It's going to come in that way. And I want a variable here to show us did it succeed in reading that or not. I'm going to go and call it We can't start with a number. So there's a Boolean to show the status of communications with just that particular module. So let's put that on the coil. Booleans. Why is it not showing up? I'm in the right program. I could have been in the wrong project. Let's check again. I made it an integer by mistake. Bad. I don't know if I can paste it over into Booleans or not, but we're going to try. Nope. I-7019 status. Again, it's an internal because it's a remote module. In this case, it's not even on the function block of the remote module. It's on the output. And there it is. Okay, so let's check again. Let's see if we have communication with that module. Always our warning about the loop. Stop application, slightly different way, not the stop sign this time. File, download, download, running. Now let's look at or associate. Now you see that the status for the communication module is good, and the counts are dithering around a little bit here. These are very small voltages, so there is some variation here. Actually, it's a rather long cord connecting the two of them also. So that's not minus 40C. That's minus 46 counts. So we do need to scale that. But we verified that we have correctly running access to an external measured value. So that's our remote I/O. So let's put it right here in the association program, some scaling of that value so we can see it all in one window. I'm not used to doing it in ladder. Let's do it in the structured text. And we're going to do it before the if ladder thing, because I want this thing to always run. So it's I'm guessing the name of the function. Normally I would look in another program and just find it. Let's see if I got the right name there. And if not, we'll see how we find names of programs. We need to do a type conversion on the expression that we're going to have. Compile will tell us if it's right or no. Must be followed by a real expression. So it didn't like that. This is how you find what function names are. I have copies of lots of CDs, so I'm going to go to a fairly recent CD that Comes with our controllers. It's also available on FTP. I'm going to go to the ISaGRAF section of it. And the I-8000 has the best documentation. I'm going to go to the English manual. And I'm going to go to the appendix where standard functions are listed. And right here in the table of contents, we've got these summaries here of the function blocks built in. Now those are ICP DOS function blocks. We want standard function blocks, so let's just page down. Just kind of scan these names and see what looks like what you want. Let's go with just real. That was listed in the standard ones. Much better. Okay, so let's go back in here and do our scaling. We're going to, now we don't want a constant in there. We want the room, what was the name of the variable? Room temp int, copy, cancel, close. Now that gets it into a real, but it doesn't yet solve our problem. So what we need to do is have a ratio of, on the bottom we want the full range, which is, from our notes, $32,767 on the bottom, 0.0 because we're doing the real thing. On the top, we want this times the full range in so the top we're having the full range in C.
Unit that is defective is at a remote site. So, for me to go out there, it's about 80 miles away. For me to go out there to verify the numbers, not going to happen today. I do have another technician going to another site where one of my other...
That compiled. Let's see how it runs.
300.
Let's see how our scaling is working. It looks like it's working pretty well. We had here minus 53 counts, and it's coming to about minus 1.8 C. And if you remember looking in the Econ utility, that was about what we were seeing.
No,
so let's go over here to Booleans.
That's definitely wrong.
The fan motor is on. Let's make... Notice every time we download it goes back to initial values. If we had just reconnected, it would have gone back, the controller would have still been running. Put it in auto, fan motor's off, pilot light. Let's light the pilot. And it's cold. So now the fan motor came on, the burner came on, and all this. Well, let's go look at the other application. We may not be able to open this one with editor windows open. Can't open editor windows open. So let's...
I'll have actually, he might be there by now. I'll have to try and call him and see
which
if
editor is open?
and I can give him
This is an editor right there. You can't be looking in the dictionary.
Well, it's getting close.
I don't know if the spy list is going to count or not. So let's go back to the WP demo window.
Okay.
And let's attempt to debug. Yes, now let's just do it.
Okay, well, I can get that.
So this would be another editor window. We couldn't start the debugging of the other one at this point in time. Notice that we're actually debugging two PLCs at the same time.
I've got no problem with
Now I want to see,
new model is,
let you see when it changes.
well, I'd rather have,
Let's open that dictionary, and it's still in the Booleans, and we're still the fan motors running. Well, let's increase the temperature of the room simulation by going to our analog output module and increasing to, say, 17 counts. Fan motor found, well, I should move the highlighting down here. The burner gas just went off, the fan motor just went off. So it responded. Let's put it back to 2 counts, and then you see it came on. So our simulated temperature changes causing the furnace to go on and off.